Woohoo, we're decaying exponentially. Yeah, this is 7.3, exponential decay. We had growth, and now we've got decay. And this is described by equations similar to the ones we just saw in exponential decay. But now what we've got is a case where I've lost my pen. Hey, we're decaying. This is going downhill quickly. We're into exponential decay. This is obviously different from exponential growth. This is where you start with something and it decays and it has that same kind of a hooked curve, but it's going down. What exemplifies this, and here in the big idea, is that our b to the gx only occurs when g is between 0 and 1. In other words, when g is some fractional amount. So our growth factor is, rather than being a whole number, something greater than 1, it is a fraction amount, and then we're raising that to some power. And so let's say our constant was 7, and our rate of growth was 1/3. And that was raised to the x. And if we had 3 intervals of that, that would be 7 times 1/3 to the 3rd power. And that's going to equal, I'm pretty sure, 7 over 27, right? Yep. 7/27. So it's going to get smaller and smaller. The greater the power, the smaller the value is going to be. And that's the idea of exponential decay. You end up with curves that go down and then hook out. That's our decay curve. So got a few terms, not too much this time. Exponential decay, what is it? And we'll come to this a little bit later in the lesson, but what is half-life? What does that mean? Take a look at our example 1. This is similar to example 1 in the textbook. We've got a student. We assume that each day, after cramming, a student forgets 15% of the words known the day before. Student crams for Spanish test on Thursday, and they have 120 words. That's our constant. Okay, example 1. We assume that each day after cramming, a student forgets 15% of the words known the day before. A student crams for a Spanish test on Thursday and learns 120 vocabulary words on Wednesday night. But the test is delayed from Thursday to Monday. If the student does not study more, how many words is he or she likely to remember on Monday? Well, what's our starting words? That's 120. We've got 120 words to start. And what's our rate of forgetting? They forget 15% of the words each day. So how many do they remember each day is the number we need. And if it's 15% are lost, then 85% are retained. So 0.85 is our retention rate. And then the number of days we have, they studied on Wednesday, then we had Thursday, Friday, Saturday, Sunday, Monday. That's 5 days. 5 days, so 120 times 0.85 raised to the 5th. That gives us approximately 53 words if the student doesn't study to replenish or restore their memory banks. So this is an exponential decay type of problem. It's often referred to within learning circles and in psychology circles regarding retention. we get this kind of behavior. Let's take a look at the next problem. This is a little bit more interesting, perhaps. It's a depreciation problem. When you buy a new car and you roll it off of the lot, it depreciates. It loses value immediately, and it continues to lose value at a very regular rate after that. So we can describe it with a exponential decay curve because we have a rate of depreciation. And here's one we have. It's in June 1953. The first Chevy Corvette was made, and it came off the assembly line, and the sticker price was $3,000. This was a lot of money back in the day for a car. It was not cheap. And suppose it depreciates by 9% each year after that. Find an equation that gives the car's value Y when it is X years old. So Y, which is going to be its value, is equal to its initial value, 3,000, times its change in value. It depreciated 9%, so it retained 91%, so 0.91, and that's per year, X. So it's 3,000 times 0.91, X is the value per year. What was the predicted value of the car in 1960? And how close is this to the actual price of a 1953 Corvette, which was $1,640 in 1960? We'll go ahead and do this calculation. So 53 to 60 was 7 years, which means that our calculation then is 1 equals $3,000 times 0.91 raised to the 7th power. We can go ahead and do our calculation and find that Y equals $1,550.28. Forgot my dollar signs. Which means that the difference between the calculated value and the actual, that's a 50 there, sorry guys, $1,550.28. So the delta in value was $89.72, which means the depreciation calculation was actually pretty good for predicting the decline in the value of the car. And remember that this kind of a graph is going to have this sort of a hockey stick curve. Well, let's go ahead and we'll graph it and see what we get. So we need a few points in order to do some graphing. X is the age of the car, Y is the value. So we'll get our, when X is 0, Y is 3,000. When X is 7, Y is 1,550.28. 1,550 and 28 cents. And let's just pick off an intermediate value in between those. So we can say maybe 3 years. And we'll go back and take a look at our calculation for 3 years. So that would just be raised to the third. So 3,000 times 0.91 raised to the third power. And that gives me $2,260. $2,260.71. Not that we worry about that. We'll go ahead and plot these points. Let me put a different color in here. So we definitely had our starting point at 3,000. We then had in 3 years 226, so that's 2,200, 2,500, so about in here. And then in 7 years we had 155, so that's about here. Now we can see that this is beginning to get this kind of a curve to it. And we could predict even further some values for the car. So let's look at this last, kind of one last question regarding the car. The car's value for the interval 0 to 7 is given here. What about in 2006? What would the price of the car be predicted to be at that point in time? Okay, we're looking at a 1953 Corvette. And what was the predicted value of the car in 2006? How close is this to the actual price of a 1953 Corvette, which was $59,900? Well, something seriously changed because it was going down in price, and now it's worth a lot more. So let's see what it would have predicted using the depreciation equation. Using our depreciation equation, would have predicted we were at 3,000 plus times, not plus, times 0.91 raised to the 53rd power, so it's 53 years later, and so that's 3,000 times 0.91 raised to the 53rd, and that gives us that it was about worth about $20.24. Not very much. So this is clearly a difference in that the depreciation calculation works for a while, and at some point it begins to not work for us. So this is the car going back up in value. What I think is particularly interesting is this car that's pictured here sold in 2014, and it sold for a number that showed some exponential growth. It sold for $660,000. Now, that's extraordinary. This is an extraordinary car. These are the original wheels for the car as built. This particular car has under 10,000 miles on it. All original materials, hardly used at all, so it reflects this in the collector's price. Okay, that is our exponential growth calculations. Let's take a look at our guided example 3. That's on page 414 in your textbook. And here we have a half-life kind of calculation. This is when something is in your bloodstream, or this is often the case, or radioactivity. But how do things deplete can be described with these calculations. In the case of materials in your system, medicines, they can go to zero. They won't stay there forever, but the calculations that describe their depletion can be described with half-life. This kind of a exponential decay calculation. So diabetes is treated with insulin, breaks down in the bloodstream quickly, with the rate varying for different types. If initially there are 10 units of insulin in a person's bloodstream and the amount decreases by 3% each minute, write an equation y to describe the amount of insulin in the bloodstream after X minutes. The amount of insulin starts at 10 units. Because 3% of the insulin is lost each minute, the growth factor is 0.97. So 97% remains. The exponential equation for this is, I'm going to draw an arrow over to here where I have more room, 10 times 0.97 raised to the x power gives me the exponential equation I can use to describe how much insulin is left in the bloodstream. The screen at right shows the starting value of 10 units. Scroll down the table to find where y is closer to 5 units. And this happens at, well, first we need to put this into our calculators, don't we? To begin to get a table to begin to see what this looks like. So let's go ahead and bust out our calculator here. Right, I got my TI Nspire emulator up, and we got their screen at right shows a starting value of 10 units, x increasing. So we need to create a table so we can do this. I think a quick way to do it is we pull up our home screen. I'm going to go to graphs. I'm going to put in my expression, which is f of x equals 10 times 0.97. So f of x equals 10 times 0.97, and I need to raise that to the x value, raise to the x, and then hit enter, and I got nothing. Oh, okay, I probably have a window problem, so let's take a look here in window. I'm going to go to trace first and do a graph trace. Okay, now I can see where my window exists here, and indeed I have my curve. I would like to take a look at a table because I don't really need to see more of this graph. I'll open that up and menu, table. I'm going to do a split screen table, and I've got for x is 1, it's at 9.7. When x was 0, it was what? Well, it was 10, right? There was the full amount. So what are we being asked? So when we want to know when there's 5 units left, which we'll scroll this down then, and we'll keep going till looks like at 23, or was it 22? So between 22 and 23 is where we had a change in, so I guess at 4.96 is pretty much 5. So we would say this happens when x is at 23. And so 5 units of insulin remains after about how many minutes? 23 minutes. Yeah, x is time, right? 23. So it's first change 4 hours into minutes. So 4 hours is 240 minutes. When x is equal to 240 minutes, then what is y equals? Well, this is still this expression, right? 10.97 raised to the 240th power. And the amount of insulin left is 0.007 units of insulin remain. So after 4 hours, there is almost no insulin left. This last question says, according to the equation, when will the amount of insulin in the body be 0? And using this equation in the body, it will never be 0, no matter how great the value of x becomes, because y will always be greater than 0. We could keep going. The graph of this curve is going to take on a shape like this, where it becomes asymptotic to the x-axis and never will ever reach it. Okay, that's 7.3. I hope this is helpful to you. Your assignment is covering the ideas and applying the math. Good luck on the mastery quiz. Bring your questions to class.